Hi guys, welcome back. So we are going to talk about the different models of the atom and atomic structure and so on. Um, we know that there have been throughout history a bunch of different models. The ones that are relevant to today's model, the quantum mechanical model, start with Rutherford's model. So Thomson and his cookie dough, that didn't really, turn out to be close to reality. But Rutherford's model was a good beginning. And so he said that we have a very small, dense nucleus that has the positive protons, and then we have the electrons being negative surrounding that nucleus. Bohr came along to improve Rutherford's model, and he said that we have this positive nucleus still that has the protons, but the neutrons were discovered by then, and so he said the nucleus not only has protons but also neutrons. So both of them are in there, and it's still very small and dense. Remember, if the nucleus was the size of like a tennis ball, the radius of the atom would be like a football field. So the nucleus is extremely small and dense. And we have the negative electrons still around, but he also added that we have these fixed orbitals or shells. Both models are based on the attraction between the positive nucleus and then those negative electrons. That attraction, we call it Coulombic attraction. Because Coulomb's law, remember Coulomb is a unit of charge. It's named after a physicist. And so Coulomb's law states that the force, whether it's attraction or repulsion, between particles, we're going to call these particles Q1 and Q2. Q is usually like the symbol for charge, is inversely proportional to the square of the distance between them. So the force is proportional to the charges and inversely proportional to the square of the radius. Now you do not need to be able to use this equation, but you do need to be able to refer to it qualitatively. And so the higher the charges, the higher that force, whether it's repulsion or attraction. Usually here we're talking about attraction between the nucleus being positive and the electrons being negative. And so the higher the charges, the stronger that attraction, and the smaller the distance, the stronger that attraction. If you think about it, if you like someone and they are pretty close to you, you see them every day, that attraction will be strong. But let's say they move overseas, they're too far away from you, you're going to kind of forget about them, right? So the attraction increases if you have higher charges and if you have a smaller distance. Now, just so you know, the charge trumps the distance, and we'll talk more about that in later chapters. But again, it is related to the charges and then also the distance. So when Q1 and Q2 have the same sign, that force is repulsive, but when they have opposite signs, it's attractive. And so this equation can be used for both repulsion and attraction. Again, here we're mostly talking about attraction between the nucleus and the electrons. Now then Niels Bohr came along, or actually we were just talking about the Bohr model. So one of the things that Niels Bohr said was that these electrons have these fixed orbitals, or these energy levels or energy shells. And he said that we can calculate the energy of an electron in its given shell or energy level. And he had an equation, which is this. And in the past, you used to have to be able to use this equation. You do not anymore. It's not even on the green reference sheet, which means you'll not be asked to use it. But I just want to go over it so that you have it in your notes for when you go to college. So this is the energy of an electron in a certain energy level. Lowercase n is the energy level. Negative, that's because there's going to be an attraction, a net attraction, right? R is Rydberg's constant. H is Planck's constant. C is the speed of light, which is also a constant. And so if you combine those three constants, you get this constant. And then z squared is the number of protons. Remember, Z is the nuclear charge, or the atomic number, so number of protons basically. So Z squared, and then N squared is the energy level squared. So this equation is the same thing as this equation. Now, we used to use this equation, but the problem with this is only it works for monoelectronic elements. So elements that only have one atom, or sorry, one electron. So things like hydrogen, that has one electron. Helium has two, but He plus means it lost an electron, so it only has one left. Li2 plus, and so on. So it's very, very limited. Again, you don't need to use that equation. This is just to show you that Niels Bohr came up with a way for calculating the energy of an electron in a certain energy level. Let's talk about emission spectra. So last year we talked about these. The idea that if you give an atom some energy, the electrons will absorb that energy and jump up from the ground state to higher energy levels and become excited. That excited state with the higher energy is not very stable, and so they fall back down, emitting that energy that they had absorbed. And when they emit that energy, they emit it as packets of light, as photons, and these photons have different wavelength and frequencies and energies, and based on where that lies in the electromagnetic spectrum, some of them are visible, some are infrared, so you feel the heat, some are UV, so you don't really see it, but you can detect it with different things. And so the emission spectra that we looked at last year was for the photons that fall in the visible spectrum. And so we looked at different elements using spectroscopy, using spectroscopes. We looked at hydrogen, for example, and we saw these 4 peaks. So let's read this together. These are things that you need to know. So the device itself that we use to get the emission spectra is called a spectroscope. And it was found that these gaseous elements emitted the electromagnetic radiation when they were heated. Or when you give them some electricity, for example, so excite them somehow, give them some energy somehow. So the light emitted consisted of discrete packets of of energy called quanta. So the energy was quantized. That means it was set amounts or certain amounts. And each element emitted a unique pattern of radiation. So the emission spectrum of each element is kind of like a fingerprint for that element. It was discovered that the release of the radiation was caused by electrons absorbing energy and being promoted to an energy level farther away from the nucleus. That's the excited state at higher energy levels. But then, because that's not stable, they release the energy as they fall back down to the ground state. Since the energy levels have a fixed amount of energy, the difference in the energy levels between them, and therefore the amount of energy emitted, is also fixed. It's quantized. It's a certain amount. So that gives a unique and identifiable emission spectrum for each element. Again, we use it like as a fingerprint to identify what elements are in a given mixture or something like that. So if you remember from last year, we talked about that if the nucleus was down here, the first energy level is pretty far away from the nucleus, and then there's a second, third, fourth, 5, 6, 7, and so on. Those energy levels get closer and closer to each other. So at higher energy levels, the difference between them is very small. At the beginning energy levels, the difference is pretty large. We can actually calculate the energy of an emission or an absorption, because remember, Niels Bohr said that we have an equation to calculate the energy of an electron in a certain energy level. So if we calculate it for the initial energy level and for the final energy level, we can subtract the two, final minus initial, and that's going to give us the difference in energy that's either being released if it's an emission or absorbed if it's an absorption spectrum. So we can calculate the energy of that jump, whether it's up or down. You do not need to use this equation again on the AP exam, but you do need to be able to compare different emission and absorption energies. Oh, sorry, that's misspelled. Qualitatively, not quantitatively. So about 6 years ago, we used to have to do it quantitatively with the equation, but not anymore. So let's look at some examples of questions they might ask you. So the visible portion of a hydrogen emission spectrum shows a violet, blue, teal, and red lines. Compare their energies, wavelength, and frequencies. And I'm going to refer to this picture that we had here. This is the emission spectrum of the hydrogen. So we have a violet, a blue, a teal, and a red. Those are the ones that are in the visible spectrum. And this actually shows you the different jumps, the different emissions. Notice that these are going from high energy level to a lower energy level, so that's how we know that that's an emission. If it was going the other way, so if it was going like from here to there, that would be an absorption. So we know these are emissions because they're going down. And these emissions are in all kinds of different places on the electromagnetic spectrum, but these four are the ones that are visible, and those are the ones that we actually see. These are ultraviolet. We can't really feel them or see them. These are infrared, so we can't see them, but they're in the form of heat. And so these are the four that we see right here. So the question asks you to compare their energies, wavelength, and frequencies. So let me go ahead and close my picture here. So we have violet, we have blue, we have teal, and we have red. So we know that in terms of energy, the violet has the most energy, followed by the blue, followed by the teal, and then the red has the least energy. In terms of wavelength, we know that the red has the highest wavelength, followed by the teal, followed by the blue, and then this has the least or shortest wavelength, I should say. And then frequencies, frequency would be like the energy. This has the lowest frequency. And then teal would be a little higher, blue would be a little higher. This has the highest frequency. Okay, and so again, remember we need to know Roy G. Biv and which end has the highest wavelength or frequency or energy, and which one has the lowest. Okay, so here it says, in the above hydrogen emission spectrum, N final is always equal to 6 for all four lines. So that means that when they fall down, the N final is always 6. The N initial ranges between N equals 3, N equals 4, N equals 5, and N equals 6. Assign each color to each initial energy level. I think this question is backwards. Oh, sorry, this should be 2. I apologize. This is 2, not 6. That's a typo here. So the final energy level is always 2. And I know there was something wrong with the question, because if it's an emission, the final energy level should be lower, right? Because it's dropping in energy. So the question is asking you which one is which color is which. So let's think about this. So if this was N equals 1, N equals 2, N equals 3, N equals 4, N equals 5, and then finally N equals 6. What we're saying is that the initial energy level, one of them is a 3, one of them is a 4, one of them is a 5, one of them is a 6. But they all fall down to the second energy level. So we're saying one of these goes from N equals 6 to N equals 2. One goes from N equals 5 to N equals 2. One is N equal 4 to N equals 2. And then the last one is N3 to N2. These are all the different emissions that we're seeing right here with these colors. So which one is which? Well, we already talked about the energy, right? We said the violet was the highest energy, right? So what does that mean? Which one is it? Well, remember these are drops in energy. That's like the arrow shows you how much energy is emitted. And so which one out of these shows the most energy dropped? And so that would be the N6, 2, and 2. Next would be the blue. It's the second highest in energy, so that would be the 5 to the 2. Next is the teal, so that would be the 4 to 2. And then finally the red has the lowest amount of energy being emitted, and so it is the smallest out of these, so N3 to N2. All right, let's look at the next one. It says, which of the following transitions emits more energy? 6 to 5 or 4 to 3? So both of these are emissions. We can tell that because we're going from higher energy level to a lower energy level, right? But which one is going to emit more energy? They're both just one energy level different. So I'm going to try to show it on my diagram here. Should have drawn a little bit bigger. But we have 6 to 5. So if I have 6 to 5, there's that 6 to 5. I'll do the other one in a different color. Let's do green. The 4 to 3 would be this one right here. So which one's emitting more energy? Can you tell which arrow is bigger? Definitely the 4 to 3 emits more energy. Why is that? That's because the energy levels are not the same distance from each other, right? They get closer and closer to each other as you go farther away from the nucleus. And so the difference in energy between N6 and N5 is relatively small compared to the difference in energy between N4 and N3. Okay, which of the following transitions absorbs energy? N4 to 3 or N1 to 2? So if we're absorbing energy, that means the electron is going to a higher energy level, right? So going from 4 to 3, that's going down in energy levels. That's going to be an emission. But going from 1 to 2, that's jumping up to a higher energy level. That will be absorption. And so the answer is the 1 to 2. Okay. Now, we give these electrons energy and they jump up to higher energy levels. But what if we give them enough energy that overcomes the attraction to the nucleus and the electron is basically ejected out of the atom? That could happen. The energy that's required to do that is called the ionization energy. So if you remember, ionization energy is the energy that you need to give the atom in order to remove the outermost electron. So if we give those electrons enough energy, they get excited, they go to higher energy levels, higher energy levels, higher energy levels. If we give them enough energy, they can overcome that attraction to the nucleus completely and turn into ions, and we remove those electrons from the atoms. To find the energy required to remove a ground state electron from hydrogen, we use this equation that we talked about. So remember, this is the difference in energy. That's how much like is absorbed or emitted, right? And so it's the energy that's in the final energy level and the energy that's in the initial energy level. We subtract them, final minus initial. Well, the initial for hydrogen, remember hydrogen only has one electron in the 1s, right, in the first energy level. So that initial energy level is energy level number 1. If we are trying to remove it completely from the atom, that means we're taking it to like an infinite energy level, right? Like we're just removing it completely out. And so that would be like infinity. And when we do that calculation, which again, you do not need to do on the exam, it turns out that we would need 2.178 times 10 to the negative 18th of a joule in order to do that. The negative just, again, means that it's an attractive force. So it's attracted to the nucleus by that amount of energy. So we need to supply it that much energy in order to remove it. One question they could ask on the AP exam is give you this ionization energy. This is for one electron, right? And could ask it how much per mole. So how would you do that? That would be a fair question on the AP exam. So let's write this down. We have 2.178 times 10 to the negative 18 joules. And you can put the negative there or not. It's up to you. I'll put it. This is per photon. Or per, I'm sorry, not photon, but per atom or electron, right? So each atom that has one electron, you need to supply it with this energy in order to overcome that attraction. So what if I had a whole mole? Well, I can put atom here, mole here, and I know that 1 mole is 6.022 times 10 to the 23rd atoms, right? And I multiply those. Now, actually, I'm going to go back and make this not a negative, because this negative tells you it's the force of attraction to the nucleus. I'd have to supply it. It has to absorb that much energy in order to overcome it. So it should actually be positive. Ionization energy is definitely a positive value. So when you multiply that together, you get a really big number. So let's round it to 4 sig figs. Just gonna say kilojoules because it's a smaller number there. All right, let's try the last problem. It says the ionization energy of sodium is 495 kilojoules per mole. So that's kind of like what we calculated here, right? This is per mole. Because your atoms cancel, end up with moles, right? So they calculated that we would need 495 kilojoules per mole for sodium to ionize, to remove the outermost electron. Will sodium atoms be ionized by a light having a wavelength of 589 nanometers? So what would I do? Well, what I could do is I can use this light, this wavelength that has this light, the wavelength of this light, and figure out how much energy that would be and compare it to this and see if it's enough or not. So we need 495 kilojoules per mole. We can figure out how much we have from the light and be able to tell. So I'm going to take that 589 nanometers, and I'm going to first change it to meters. 10 to the 9th nanometers is 1 meter, so that gives me 58.9 times 10 to the negative 7th meters. Then, since I have wavelength and I need energy, I have to stop by the frequency first. So I'm going to say C equals lambda nu. So 3.00 times 10 to the 8th meters per second is equal to 58.9. I'm sorry, 5.89, not 58.9. Here we go. Times 10 to the negative 7th meters, and then solve for nu. Nu here ends up being 5.09 times 10 to the 14th hertz or per second. And then I can use E equals h nu. So the energy would be Planck's constant, 6.626 times 10 to the negative 34 joules times second, times my frequency, which I just got, 5.09 times 10 to the 14 per second. And my energy ends up being 3.37 times 10 to the negative 19 joules. Now, I did get some energy, but I can't really compare this energy versus this energy. Why not? Because this is in joules, and this is in kilojoules, and this is for 1 photon of light, whereas this one's for a whole mole. right? So this is per photon. So I have to convert one of them to match the units. So either I convert this to kilojoules per mole, or I convert this one to joules per photon, right, or per atom. So I'm going to go ahead and convert this to kilojoules per mole. So I have 3.37 times 10 to the negative 19 joules per photon. So first I'm going to go from joules to kilojoules. I'll put joules here, kilojoules here. 1 kilojoule is 1,000 joules. So that way my joules cancel. I'm kilojoules per photon right now. So the next step, I'm going to go from photons to moles. So I need my photons to cancel, so I'll put photons here, mole here. 1 mole of anything is 6.022 times 10 to the 23rd particles, whether they're photons or atoms or eggs or whatever, right? So that cancels. I end up with kilojoules per mole. I'm going to go ahead and calculate that. And I end up with 203 kilojoules per mole. So this light that I have can supply 203 kilojoules per mole of energy. Is that enough to ionize sodium? The answer is no, not enough, because I need at least 495 kilojoules per mole, and I only have 203 kilojoules per mole.